All right. Let's get things started. Hey guys, hopefully you guys are okay and slept well. This is another lecture for 1206, or I should probably say more of a Q&A session. So I assume you guys have all looked into integration by substitution. Is that the lecture? Yes. So, okay. So maybe, first of all, any comments, questions, concerns? Just to begin.
I had a question about the end of the video with the examples.
Yes.
So I noticed sometimes you substituted u under the radical and sometimes you substituted u squared. So how do you tell when you should do which?
Either one is fine. It's just that one might be easier than the other. So in the sense that, let's look at one. Let's look at this example. X cubed over the radical of 1 plus x squared dx. Okay, so one is just kind of a refinement of the other one. And so let's look at options here. So one is do a u equals 1 plus x squared. And let's do that versus with u squared equals 1 plus x squared. Okay, so they will both work and they'll both get you to the answer. But let's see, this one has potential benefits in terms of how annoying it would be. So let's do a regular U substitution because this part here is the part that will make it complicated. So you'll probably know that you want to actually substitute that guy. So let's start with that. Our du would be 2x dx, right? Now, the x cubed, and remember one of the criteria, which is kind of a very relaxed criteria. It's not going to work all the time in Calc 2, but you want to kind of see that you can find your du elsewhere in the function as a factor. And so you can see that for this example by just rewriting your x squared as rewriting your x cubed as x squared times x. So this part is right there. So it means that this substitution is going to work. It's a good substitution. And so everything seems hunky-dory. So let's just actually continue. What we would have to realize here is that I can replace this entire thing. So this means that 1/2 du is going to be your x dx. And let's just start to swap everyone out. So our integral would actually become x squared times 1/2 du over the radical of u. And now you'll notice that you'll have this x squared to deal with. But you can go here, you can solve for that x squared. And you can actually plug that in. So this would actually be, what did I say it was? I didn't sleep all today. U minus 1 over the radical of u times 1/2 du. So that's what our integral would become. But of course, you think of this as u to the half. And so this is really u to the 1 divided by u to the half. So this is u to the 1/2 minus u to the minus 1/2 du. Power rule applies to these guys, so I can add 1 to the power, divide by the new power, add 1 to the power, and divide by the new power. So now my u was 1 plus x squared, so this is 2/3 1 plus x squared to the 3/2 minus 2 times the radical of 1 plus x squared plus c. And that is your answer, okay? So that's completely valid, it's completely fine, nothing wrong with that solution. Now, let's look at the other option. Why would you want to do a squared substitution? Wouldn't that make it more complicated? On the contrary, it will actually make it a little bit easier to execute because the square, putting a square under the radical, they'll kind of cancel out algebraically. So with this, you would differentiate both sides. So that's 2u du is equal to 2x dx. And again, we have the x dx part in our derivative, in our integrand, right? The factor is right there. What this means is that u du is going to replace that x dx. And so our original integral will become the following. So the x squared part is going to become, well, I can solve for it from here. I'm bending the arrow up because the chat box is in the way. You probably can't see it on your screen, but so the x squared is going to be 1 minus u squared. Oh, this was.
I have a quick question about that too.
About what I'm doing so far?
Yeah, like when we have to solve for the x, is that just when it won't be canceled with the du, or like what the dx is technically from the derivative? Like when we plug in for dx and stuff, and there's still an x that couldn't be.
You could solve for it that way. It'll work out either way.
Okay.
So even here, if I had solved for the dx, and I get u over x du, once I plug this guy in, he's going to cancel that x anyway. This x here would get canceled. And so if I leave him here and just swap, so swapping out the entire thing, or plugging this in with an x in the denominator to cancel that out, they end up doing the same thing.
Okay.
So sometimes I just want to like find a part that I can just literally swap in. Now, that being said, start swapping in. What we're going to have here is the x squared is going to be u squared minus 1. The x dx will become u du. And then in the denominator, I have a u squared under here because that's what I substituted, and it kills the radical. So that just becomes u. And now what you realize is going to happen is that the u's will just cancel. And so this would actually equal to the integral of u squared minus 1 du. Right? So now this is the benefit here. If you compare this line after I kind of cancel everyone out to this line, like which one would you rather have dealt with? You know what I mean? So the u squared substitution kind of makes your, once you get to the u version of the integral, it looks nicer. So then with this, it's much easier to apply the power rule. I don't have to worry about radicals. I don't have to worry about half powers and adding fractions and things like that. That's u cubed over 3 minus u plus c. And now I just remember that my u is actually the radical. U is actually 1 plus x squared to the half. And so you get the same answer, right? These are the same. For here, the 2's cancel out. This 2 cancels with that, cancels with that. Okay. So it's not like one is completely different from the other. The difference is more of an aesthetic or slash make my calculations easier kind of thing. Out of personal preference, I like this one because it's just nicer, it's cleaner. But this one is a pretty typical approach for a Calc 1 student. I just thought I'd show you guys this. Because in Calc 2, you do things like this more often. You kind of modify the kind of thing you're substituting. You don't always substitute just a single variable. You learn other techniques in the next class where you substitute all sorts of things. So I kind of piggybacked off that and said, well, we can start out by substituting things just to make our lives a little easier. So for example, if there were, so another example, if I had something very similar, let's say an x cubed over the cube root of 1 plus x squared, I could do something similar. So I could do u equals 1 plus x squared, or I could actually do u cubed equals 1 plus x squared. So the whole point is me doing a substitution that's going to end up making my life easier at the end of the day, which is actually the whole point of substitution. You want to substitute something so that your complicated integral looks simpler. But by modifying your what you're substituting, you can make it even look simpler. And so ultimately you'll get to the same answer whether you I'm just always going to do u, that's fine. You'll ultimately get to the same answer. But there are ways to make things a little bit cleaner, make the algebra and the arithmetic work out a little bit nicer. And so that was the difference between the u squared versus the u substitution. No one is any more correct than the other one. So I was just showing you an option that you have. Now there are some students which at this point doing something like this totally confuses them, and it's fine. Just stick with this and forget that. You don't have to know something like a u squared substitution. It's just something that would make your life a little bit nicer when it comes down to actually computing the other integral. Hopefully that kind of clears up your question. Did I answer your question?
Yes, that's good.
Yeah. So it's just a variation on the same technique, and the variation is for just aesthetic reasons almost. Like instead of integrating a u to the half power, I'd rather integrate a u squared. You know, it's that kind of thing. Now, and maybe I'll show you the thing that you asked about earlier. So maybe I'll also talk about this. So yesterday when I was teaching, I recommend always solving for the dx. So I want to show you that that actually wouldn't have made a difference. Solving for dx. So solving for dx is just another variation that really only makes it psychologically easier for people to handle. So if I had, let's look at the same example, x cubed over the radical of 1 plus x squared. And let's go with the regular u, 1 plus x squared. Your du would be 2x dx. You could here solve for your dx, as was recommended, and then you're just going to take this expression and you're going to plug it in here. Now, what is going to happen when you do that is you're going to have x cubed times 1 over 2x du. And in the denominator, you're going to have, well, radical u. And what's going to happen there is that this x will cancel into the x cubed, leaving you with x squared. And then once you see the x squared there, x squared, no bueno, right? This is a problem. So we need u's. There should only be one variable. So that's when you go back to your substitution equation. Anytime when you have any of the variables left over that you don't want, go back to your original substitution equation and kind of solve for them. So we can solve here. You would get that your x squared is actually u minus 1, and then you come back and you plug that in. But again, you'll notice that we get back to that same line. This here is the same thing that we had. I don't know if this will do. Same thing we had there, okay? So it's the idea that I could literally just swap out a whole thing times the dx and then change everything afterwards. Or I can just always solve for the dx, replace the dx itself, and have the other part cancel everything out. So these are all variations on the same technique. I showed you guys this one where I say solve for the dx all the time, just because statistically speaking, I find more students find this part conceptually easier. They don't want to have to substitute big expressions. They just want to plug something in and then cancel afterwards, and have the actual algebra and arithmetic help them figure out the last integral, than as actually trying to like move these big chunks of things. So it's just another option. You'll end up in the same place with all of these. So I would prefer this version, and the typical Calc 2 student would probably also prefer this version. But yeah, these guys are they're all as good as the next one. Other questions?
Do you see where it says the example, then it's the integral of x to the third? Then you wrote u equals 1 plus x squared, or u to the third equals 1 plus x squared. Where did you get the u to the third?
Oh, so this is just because I saw the cube root here.
Oh, okay.
Right? So I want a cube to kill the cube root. If this was a 5, I would put a u to the 5th, and so on and so forth.
Okay, got it.
The point I'm trying to make between just always saying u equals something versus something else equals an expression is that you can tailor your expression to make the thing even easier. So if I have a radical here, I know eventually I'm going to have to turn that radical into a half power. And so I don't really want to do that. So what I do is I throw in a square there to kill the radical, so I don't have to deal with the radical at all. So I would end up with a situation like this instead of a situation like this, right? So by a similar vein, if I had this cube root here, I'm like, well, me doing a u squared isn't going to make that any nicer. I'm going to have like a 3/2 power down here. So put a cubed, right? If this was a 7th, I would put u to the 7th, right? And I'm tailoring what I'm substituting so that while I'm substituting, it's further simplifying the expression for me. But again, like I said, you don't have to worry about doing that at this point. It really only makes your calculations a little nicer. If conceptually something like that is something that you're not sure that you'll figure out, it's totally fine going with the regular, just plugging U for something. And you'll work a little bit more at the arithmetic part of the problem, but if you're more likely to not mess up getting to this step by going this route, then I would say stick with that route. Yeah, so that discussion at the end there was just an optional one for people who like things a little bit cleaner while they're working things out. They can use their substitution to simplify the integrand even further than a regular U substitution would actually do. Other questions?
I have a question about class grades.
Yes.
Do you plan on curving like the class grades at the end of the semester?
Well, I think there's already a curve built into the thing, into the grade system.
Okay.
So I wouldn't say curve it specifically, but I'll definitely weigh things differently considering everything that's going on. So I know that you guys haven't been able to do as many quizzes as I would like and all that good stuff. So yeah, I'll grade things in such a way to give everyone the benefit of the doubt. So.
Okay, thank you.
And yeah, when the final comes around, especially speaking about that, the final is going to be more cumulative. If you can really show me that you've improved on what you've done up to this point. So let's say you did test one and you really messed up on this problem where you had to find the derivative by definition or whatever, by the limit definition. Like if you can show me on a final that you know how to do that now, I'll probably just kind of conveniently forget that you didn't know how to do it on test one. You know what I mean? So things like liberties like that are the ones that I would take. Like I don't think I'm going to impose an additional curve right across the board, but I'm going to be looking closer on the individual to see that, is this person learning? Are they improving? Do they do better than last time? So
is the final cumulative from?
Yeah, the final is everything. So the final is going to be kind of like a test one and a test two stuck together.
Okay.
And if I'm not mistaken, I believe I have a mock final on the website. If not, I'll probably put one up. But I think I do. Let me actually check. So yeah, I do have sample finals. So you'll know what when it comes time to prepare for that. Don't look at those finals now, but when it comes time to prepare for finals, I'll probably start looking at those. After you do test two, I would brush up on the test one material and then start going into your final review. So just take a day, brush up on test one material, then start studying for the final. And there are 3 mock finals on the class webpage. I think there's only one that has a solution, but hopefully by you get to that point, you won't need me to give you solutions. Hopefully you at the very least be able to check your own answers, because with all the craziness that's going on right now, I don't think I'm going to have time to do all these final exam solutions and post them and all that good stuff. So But yeah, the final is cumulative in the sense that it will be sort of a combination of test 1 and test 2. So that being said, if you mess up on test 1 and or test 2, the final is actually going to be a chance for you to redeem yourself. It's essentially like both of those exams stitched together. And it is also like twice as long. So the final is going to be like 2 hours and change, 2 hours and 15 minutes, something like that. Whereas each of your exams were 1 hour. Other questions?
Can I ask a question about a previous lecture?
Sure, yeah, shoot.
All right. So it's for the computing definite integrals and finding their derivatives lecture.
Yes.
The part where you take a function that equals an integral and then you find the derivative by plugging in x.
Yes.
I guess I'm just confused as to how like that allows you to find a derivative.
So this is the fundamental theorem of calculus part 2. Some people call it part 1, but the way I presented it in class was part 2. And it says that if you have part 2, and it says that if you define a function as an integral with some constant up to x of f of t dt, this means this function is measuring the area under some curve, starting from point A, and it increases to point X, right? So we really cared about areas. So someone invented a function that measures the area under a curve. So they write it as an integral, okay? So for example, if you plug in 1 into this function, the output is going to be the area between A and 1. And if you find f of 2, what is f of 2 of this function? Well, it's going to be the area between A and 2, right? So when you define a function as an integral, basically what you're saying is we are creating a function to track the area under the curve on the interval. Well, I put C here. Let's call this A. From some point A up to a variable point X. So my right endpoint, I allow it to move, right? And so I define a function that measures that area. And so someone might say, well, how would I differentiate such a function? So that's what the fundamental theorem of calculus says. It says to find the derivative of this guy, you literally just ignore the integral. And you plug in the top number. And basically the idea behind that is the derivative is the opposite of the integral. They cancel each other out. Almost. Going in the other direction, the integral, when you integrate, you get a plus c. So it's not completely reversible in both directions, but the derivative reverses the integral. The integral does not fully reverse the derivative because it can lose some information. But this is actually a part of the fundamental theorem of calculus that says derivative and the integral are opposites. They cancel each other. So the idea is, if I put a derivative in front of an integral, the essential idea is that they actually cancel each other out, and I'm left with the function by itself after evaluating it at the top point, right? So that's what the fundamental theorem of calculus says. And then we have some, I think you'd call them corollaries. And I always forget how to spell it. I think it's 2 R's and 1 L. You know what I mean. It's saying it's spelling bee. This is Calc 1. Okay, so there are some corollaries. So if I want to take the derivative of an integral where the top is some function, it's not x. It's not just x. Then the chain rule takes effect. You plug that function inside and then multiply by its derivative. So that's one corollary. So this is just an application of the chain rule. And then there's another corollary that says, what if we have two functions? So there's like a g of x down here, and there's an h of x up there. Then we can actually split the integral. And you don't even have to really know about doing this part. You don't really have to write it out, I mean. Then what you can do is you can actually split the integral, because that's a property of integrals. So you can go from g of x up to some constant, plus then you can go from that constant up to the h of x. And then what you can do is, there's another property that says you can flip an integral by putting in a negative sign. And so now what you have is, for each of these individually, you have this rule taking effect. And so pretty much what that means is, you're going to take the f, plug in the top number or the top function, multiply by its derivative, minus, you're going to take the f, plug in the bottom one, and multiply by its derivative. So these are, now why we can do this is because the fundamental theorem of calculus says that this is the case. The derivative is going to cancel out the integral. And if there's not just an x here, you have to apply the chain rule while taking the derivative. So this is a fact that we know. And we know that we can do this as a fact that we know. That applies by the chain rule. And the first idea, let me actually rewrite it nicer here. And the first idea that says the derivative for constant up to x, f of t dt, this is equal to f of x. That is the main fact that we know. That is the guy that we know that's true from the fundamental theorem of calculus. So I proved why that's true in class. You don't have to know the proof, you just have to know the facts. So if I were to ask you, and normally when I do this, I'm going to give you a function that it's really hard to integrate on its own. So for example, I might ask you, what is the derivative of, say, 5 up to x cubed of the sine of t cubed dt, for example, just a silly example. Now, some students might be tempted, and whenever this can work out, it will actually give you the same answer, to actually do this integral and apply the first fundamental theorem of calculus, plug in the bottom minus plug in the top, then take the derivative. Turns out doing that here, though, is impossible, because sine of t cubed has no antiderivative. So this is just a matter of, you should not have to worry about actually doing the integral. The derivative should cancel the integral. Only thing that's going to happen is you're going to take that x cubed and you're going to plug it into the t cubed. And then you're going to multiply by the derivative of the top, and you ignore the constant bottom. So that's your answer. So the derivative of this is just take this, plug it in, multiply by a derivative. That's essentially what it comes down to. And if I were to have something like cosine of x up to x cubed of the sine of t cubed, and I actually find the derivative of that, what you're going to do is you're going to plug in the top number, which gives you the x to the 9th, multiply by the derivative of the top number, minus plug in the bottom one, multiply by the derivative of the bottom. And that's going to be your answer. So those questions are really testing. Do you know these three boxed equations? It's pretty much what we're going to say. Now, there's a lot of conceptual clout behind them, and it's a very important fact to know these three things. But in the grand scheme of things on a test, these problems should not give you too much trouble. It's just a matter of, do you know how to just, it's literally like a template, plug and chug. So if you see a function here, put it there and multiply by the derivative. If you see a constant here and an x there, put the x there and ignore everything else. If you see two functions, put in the top function, multiply by its derivative, minus, put in the bottom function, multiply by its derivative. So these are just some facts that you should know how to actually compute them. But the point of all this, it's really just saying the derivative and the integral will cancel each other out. But we can also use this to do some nice calculations a lot easier.
Could you just scroll down to where there's two functions, that equation?
The example or this one?
Yeah, just that one.
Yes.
Okay, thank you.
Okay. Other questions? So yeah, like I said, our lecture material, what we're doing goes up to lecture 39, which means by, say, next Wednesday, you should have consumed up to lecture 39. And most of the new material is done in lecture 38, but lecture 39, I believe, provided some extra examples. So that's why it might be nice to watch a part of lecture 39. So ignore lecture 40. That's not going to be something that you're responsible for. And I think between now and Wednesday, you should be able to do, get through all of those guys.
I have another question from
Yep.
the same lecture.
Mm-hmm.
The last example, that's p of x, and then that has, it's from x squared plus 1 to x cubed.
Hold on. So it said p of x equals
And then
x squared plus 1.
yeah, and then
Yeah.
x on top.
X cubed.
And then it's sine of t over t dt.
Yeah.
So then this one we solved by breaking up the integral into sub ones.
Yes.
Could we also just solve it that way with the two functions and then just like plug in the top
Yeah.
one?
So in class, I actually worked through this with you. So when I was doing that example, actually worked through this.
Okay.
But it'll actually always end up the same spot. It'll always end up looking like this. So yeah, you could do this the same way. Like if you wanted to find p prime, it's take the function, plug in the top number, and multiply by its derivative, minus, take the bottom function, plug it in, and multiply by its derivative. And you'll notice that that was the same answer.
Yeah, okay.
So in class, I actually went through these steps with you because I didn't just want to give you the formula. I wanted to show you where that formula came from. So, so yeah, I just worked through this while doing that example. but it always ends up here. As well as there's benefit to knowing, like if you know one formula and there's another thing that depends on it, there's benefit to knowing the steps to go from one version to the other version. It builds up your mathematical maturity. And so I'll probably encourage people to do this as opposed to just jump straight from this to that. But you can just do this if you want. But in class, I just work through the steps as to how we get from here to there. Because at that point, all that you guys knew was, I believe I told you these two things at that point. And so how do we use these two things to figure out that thing? And so I went through the steps with you. So what are you guys thinking for the summer and fall? Are you guys going to register for classes?
I was
Are you
supposed
guys
to go abroad. So
come again?
try to go abroad.
Oh, you're going to be away. Away.
I'm
Okay.
trying to go. We'll see.
Okay. If you don't, would that be something you consider? Because I'm pretty sure the entire summer session is going to be online. I don't know about the fall, but
If they don't let me go abroad, then I'll be at Fordham in the fall if they let me there. So we'll see what's open.
okay. Is this one of those study abroad for like a year program kind of thing?
Yeah, it's the full semester.
Oh, nice. So yeah, that being said, you guys have all the mock tests up, and you have mock finals. I'm not going to change the format at all. You know, given everything, I'm not going to turn on a dime right now. So yeah, you guys should be fine if you're following along with the lectures and asking me questions and da-da-da. So yeah, so you guys can, hold on, let me just make sure. Yeah. So I mean, even now, if you're good with the applications of derivatives and integrals, like right now, you guys actually know enough to do test 2. Like test 2 only goes up to substitution. So test 2 is going to cover just calculating various integrals, computing, evaluating them, including using substitution, optimization, motion problems, the mean value theorem, absolute maximums and minimums, derivatives of definite integrals, which is what we were just talking about, using linear approximation to approximate some value, using finite and infinite Riemann sums to find an area. And then other than that, there are just some bonus problems. So all of those you guys currently know how to do. So you guys can start doing the mock test 2s like right now if you wanted to. So for test 2, I have a general review, which you should go through. And then I also have an old test 2. So yeah, as I mentioned, the test 2 that the class, which I recorded the lectures in, that's I have the test that they took. So I posted that on the class website. So go through the test review, see how you do, see where your gaps are, try to brush up on them, and then take the old test 2 that I gave in spring. And hopefully between those 2 experiments, you should have filled in all your blind spots. And then I wouldn't start worrying about the final until after test 2. So after Wednesday, then start going over the test 1 material, because you guys would probably have forgotten a lot by then. And then try, at least by the end of the week, to get through 1 or 2 of the mock finals. And maybe try a third. In terms of that being said, I don't think there were any changes made to the final exam schedule. I checked like 2 days ago. But as far as I know, the schedule is roughly the same. I mean, I can compare again. Yeah, so for section R03, I think it's May 6th. So that would be a week after test 2, which I think is enough time if you can brush up on test 1 material. You should be good on the second half of that final, which is the test 2 material. And then section R04 would have it on May 8th. So you guys have 2 more days in section R04. So R03 has it on May 6th, and R04 has it on May 8th. And R03, that is the section that has recitations on Tuesdays.
Did you say what time we're gonna have it yet? I'm sorry.
Yeah, it's 9:30 a.m.
Okay.
I think they're both 9:30. Yeah, so R03 is Wednesday, May 6th at 9:30 a.m. R04 is Friday, May 8th at 9:30 a.m. And the final is going to be like 2 hours and 15 minutes long, 2 hours and change. And it's going to look like a combination of test 1 and test 2. So after studying for test 2, so after taking test 2, which by Wednesday you would have completed that, Tuesday or Wednesday, then I would start going into studying for finals mode. And you should be okay in getting up to scratch in a week. You have 3 mock finals to do it with. And yeah. Anyway, we're pretty much out of time. So unless there are any other questions, I think we can go. And I'll post the PDF of this in the description of the Q&A video. So again, I'll post the Q&A video and the PDF of this is below. Which in fact, what we did yesterday was posted and the PDF of that was below, even though we didn't really do anything yesterday. So I scribbled some things here, spoke about some things, and I wrote down some announcements. And yeah, but I still posted this PDF. I'll post the PDF that we did today, as well as this video in the Q&A series. Okay. So hopefully that was helpful and I answered all your questions up until this point. Right now, you guys you know enough to go through test 2. So, yeah. So are we good? You guys are really silent.
Yep.
Okay, all right. So we'll end there today. By this evening, I'll post this the PDF for this as well as the video. A link to the PDF will be in the video description. And yeah, if you have any more questions, you can let me know. You can even save that for our Friday session. So I'll see you guys back here, same time, same bad channel on Friday. Good luck, everybody, and stay safe.
Thank you.
All right,
Thank you.
take care. Ciao.